Now let's talk about the other problem that a typical problem in the eyes that people have, which is hyperopia. So it's just the opposite of myopia, and the problem is that the eyeball is a little shorter than it should be. Okay, so the normal size of the eyeball will be something like this, so the retina will be this distance behind the crystalline lens, but for a hyperopic eye that is closer. So if you have an object at infinity, the light rays of that object with a relaxed crystalline, that is, they would form on a normal light, they would form on the retina. Normal light can see objects at infinity, but they don't cross, or they don't focus on the retina of the hyperopic eye, so therefore it looks blurry at this point. But that's not the end of the story, because if the person can accommodate, if the person can squeeze that crystalline lens, shortening the focal length of it, then this point is going to move back. Right? So if you squeeze the crystalline lens, you shorten the focal length of it, and that point is going to move forward, and it's going to intersect the retina, and that will be, you will be able to see clearly the object. So an object placed at infinity for a hyperopic eye can be seen clearly. You can focus on that. The only problem, of course, is that your crystalline lens is already squeezed, where it should be relaxed, right? To focus on an object at infinity, you're already having to work your eye to see an object at infinity. So part of the range that the crystalline lens can cover, you're already using it to focus at infinity. So that means that you're going to come up short on the other side. That is, when the object gets close to you, you're not going to have enough room to accommodate for that, because you already used part of the room that you have, the accommodation that you could have, you're already using it for an object placed at infinity. So as the object gets closer and closer to you, starting at infinity, the crystalline lens has to accommodate, so it gets compressed a little bit, and you get the image form on the retina. As you start getting the object closer and closer, the crystalline lens, the image of the object, it's going to form behind the retina, so the crystalline lens gets squeezed a little bit more, so the image moves back on the retina. You keep moving this object, and the crystalline lens has to squeeze a little bit more, right? But then, of course, there's going to be a point where the crystalline lens cannot be squeezed anymore. So that means that your near point is not going to be the normal 25 centimeters. The near point is going to be something bigger than 25 centimeters. Okay? At this point, where the object is at this distance from your eye, you're already using your maximum accommodation possible for the crystalline lens. And you got it just barely to focus here. If you bring a little closer, that point moves back, and you don't have any more room here to adjust. So a hyperopic person has a near point that is bigger than 25. Can see all the way to infinity, but closer things, that's where the problem is. So how do you want to, how would you correct for this? You want to be able to see objects that are 25 centimeters from you, just to have normal vision, right? So if you placed an object here, the lens that would help you with that problem is a lens that would take an object here and produce an image at the near point of your eye. Right? Remember that if you put an object here, you can focus that, but barely. That's the limit. So if you place an object even closer than that, this lens, if it were able to produce an image here, then your eye will be able to focus that. So that's the job that you want this lens to do for you. Right? To move, to have an object here and have an image of that object that is behind the object. So remember that, contrast that with the myopia case. In the myopia case, you want to have an object that is way away, and you want to bring it closer to you, right? So you can see it clearly. For the hyperopia case, you want to have an object that is close to you, and you want to move it further back, because you cannot see that close, things that are that close. All right? So if that's what you want to do, then the focal length of the lens that you want that to do, first of all, it should be a converging lens. You want to have an image of the object that is upright, and it should be behind the object. If it was a divergent lens, where would the image of this object be? It would be over here. That would make things worse, right? You could not possibly focus on an object that is even closer than 25. You can't even focus 25. So you have to use a convergent lens. And the convergent lens is acting sort of like a magnifying glass. And it pushes the image back to the place where you can focus it. So that's going to be a positive focal length, and the object placed at the near point of a normal person will have a distance to the lens of 0.25. And the distance, you want the image of that object to be formed at a distance that is equal to the near point of the hyperopic eye. And that's going to be on the left, the upstream side of images. So that goes with a minus sign. So from here you solve for the equation 1 over the focal length that you use, called the diopters of the lens that you're going to use to correct for that. So the diopters will be 1 over 0.24 is 4 minus 1 over the near point of that person. So notice that the range for the diopters of a hyperopic eye goes all the way from 0 to 4. Right? If the person has a near point that is normal, then this will be 4. 4 minus 4, that will be 0. So a normal person is here. The worst case scenario will be when your near point is actually at infinity. That means the person cannot focus anything. Right? So that will be the worst case scenario, when the near point is actually way over there at infinity. So that will be 4. So this will be sort of blindness. I mean, you see the light and everything, but you just can't focus.